Net primary productivity is also influenced by environmental conditions and the types of species that are present in an ecosystem. The climatic controls over NPP are mediated primarily through the availability of below-ground resources. So here is a figure that shows net primary productivity across a wide range of ecosystems. We're going to take a look at NPP as a function of precipitation and temperature. So this would be annual precipitation, millimeters per year, and mean annual temperature. So the average temperature of an average day in degrees Celsius. So here on the left panel shows that NPP increases with precipitation to a certain point, and then it's flat to declining. So for most ecosystems, up to almost 3 meters of rain, increases in precipitation increase NPP, at least on a geographic scale. And then warmer ecosystems also have greater NPP, and this holds across a wide range of ecosystems. So together, wetter ecosystems and warmer ecosystems, at least up to a certain point for precipitation, are going to have greater amounts of NPP. Across ecosystems, if you look by biome types, there's over 10-fold variation in NPP. So just looking at the above ground component of NPP, on the high end are tropical forests, which are estimated to have over 1,000 grams of biomass produced per meter squared per year. In contrast, tundra is less than 100 grams of biomass per meter squared per year. Below ground, the numbers are pretty similar. Over 1,000 for tropical forests, approximately 100 for tundra. Again, 10-fold variation. So in total, over 2,000 grams, 2,500 grams at the high end for tropical forests, and less than 200 grams per meter squared above ground and below ground together for tundra. The percentage of the NPP that's below ground is roughly half across ecosystems. This number for crops, I'm not quite sure I would believe. So having only 80 grams per meter squared per year below ground for crops is pretty low, and let's not think about that. So, but still, if we look at total NPP for ecosystems, over 2,000 for tropical forests, less than 200 for tundra, that's a factor of 10-fold variation across biomes. And again, it tends to be the warmest, wettest biomes and the coldest and driest biomes that have the most and the least NPP. Now, the authors state that if you take a look at interannual variation, so we were looking at geographic variation, comparing sites that differ in their mean precipitation or their mean temperature. But we can also take a look at what happens if a given year is wetter or drier and what the consequences are for NPP. So dry sites show the greatest sensitivity to NPP when we have interannual variation in precipitation or rainfall. So if you're to take a look at rainfall among years, you'll have wet years and dry years, for example. And for sites that are dry overall, you get a big response in NPP if it's wet. And NPP is greatly reduced when it's dry. And it's the dry sites that are thought of as being the most sensitive to interannual variation in precipitation. This here is one of the figures that is most prominent in determining that pattern. On the x-axis, we have precipitation. On the y-axis, we have above ground net primary productivity. Units are millimeters per year, grams per meter squared per year for NPP. Each of these lines represents an individual site. If you look across sites, this is the pattern that you see, which gives you a geographic pattern between precipitation and above ground NPP. But if you look within a site, some sites have a relatively steep slope in its relationship between precipitation and NPP. So, for example, there are some years that are relatively wet and some years that are relatively dry, and there's an average. And so if you take a look at the relationship between NPP and precipitation for a site, the slopes of these lines tells you the responsiveness within a site to variation in precipitation that happens interannually. And the conclusion that was drawn from this work is that you have steeper slopes on average on the dry end than at the wet end. And I'm going to be honest here, and I'm going to star this one. It's something that I don't necessarily agree with. So all of these sites that show relatively steep slopes are grasslands. And in this case, measuring ANPP is pretty simple because you don't have to measure wood. That being said, there are grasslands that have relatively flat slopes. So it's not necessarily a grassland or precipitation that determines whether it's a steep slope or a flat slope. And you can see if we don't understand why these slopes are pretty flat, which means at this site, for example, when you have increases in precipitation, you get no increases in NPP. Being grasslands, you don't have to measure wood. And these 4 sites over here are all forests. And these 4 sites didn't do a good job of measuring wood. So the variation that you see in ANPP is mostly leaves and litter fall. This site, for example, that has a negative slope is Barrow, Colorado Island in Panama. And here, there's no estimates for interannual variation in wood production. And wood production is a significant component of ANPP. And so, although for the numbers that they had, they gave you a slope that said these wet sites have very low sensitivity to precipitation, those didn't include wood. And it's quite likely that you get a lot more wood production when it's wet compared to when it's dry in a site like this. We just don't know. So this half of the graph, I would say, we're uncertain about the responsiveness to precipitation that happens in wetter sites. This side of the graph does seem to hold that you get a pretty constant slope if you look, but there's outliers here. We don't know how prominent they are or how often they occur, and we don't know why a site like this would not have any responsiveness. That's a pretty long explanation, but I think it's important to realize that a lot of these patterns that we see still need to be questioned, and we still need to take data to better understand them. So in general, what's thought is that when you look within sites and the variation that you see in NPP, in dry years, it's thought of as those sites being moisture limited. So when it's dry, you add moisture, you see greater responses. And in the wet years, there should be enough water to grow, but often nutrients can be the limiting factor in the wet years. So there's shifts from water limitation to nutrient limitation. But I'll admit, I still think there are problems with generalizations like this. So even though the book says that it's a generalization, and it's important to know what the current generalization is, that when we look at how nutrient dynamics work, and we'll talk about this in a later chapter, that watering is also like fertilizing. So this is a graph from 1974. And essentially what they did is they took a look at how much nitrogen was made available from soils as soil water changed. So from an optimum soil water content, which wasn't necessarily 100% saturation, but if you look across dry soils and you look across wet soils, the amount of mineralization actually increases, and it increases pretty linearly. So what happens in a year when there's more rain? If there's more water there, your average soil might go from 20% to 60%. And so your nutrient availability also increases. And it's really hard to determine in a wet year versus a dry year. Yes, you have more water that's available, but are the plants responding to more water being available or actually more nitrogen being made available? So partitioning out water limitation and nitrogen limitation and how individual ecosystems respond is pretty difficult. Cold sites, though, also show another paradox that you wouldn't necessarily expect. In tundra, NPP increases more in response to the addition of nitrogen than to experimental increases in temperature. So tundra is a cold place, and we know that there's a positive relationship between mean annual temperature and NPP. Despite this, from that relationship, you would think that moving a site from cold to warmer would also increase NPP. But it turns out you get a lot bigger responses in productivity if you add nitrogen than if you increase the temperature. Part of the reason is that temperature also controls nutrient availability. And so if you warm up a site, you're actually increasing the amount of nitrogen that's being made available. And if you increase the amount of nitrogen that's being made available, but hold temperature constant, you get even bigger increases in NPP. So watering is like fertilizing. Warming is often like fertilizing too. Separating out the proximal and distal limitations to productivity are pretty difficult to do. The patterns that across sites seem to hold pretty well, but why that happens is still something that we do not understand that well. So, in review, GPP is governed by leaf area and length of season, and that part we know pretty well. It's the sites that have the greatest amount of leaf area, and that leaf area is displayed for the longest amount of time, that really have the highest GPP. When we think about NPP, it's really the below ground resources that seem to be determining the large temporal patterns and the large spatial patterns that we see across ecosystems in NPP. And so in this sense, if we want to understand productivity and how much net primary productivity there is within an ecosystem or across years, we have to pay special attention to below ground resources and how much water and nutrients are available to plants.